Alright, so we're going to continue exploring average rate of change in this video. And as we learned in the last video, average rate of change consists of a difference quotient where we do f of b minus f of a over b minus a. And to get us started, we're going to jump into a pretty straightforward average rate of change in part A and in part B. You'll probably want to have a calculator handy as you work through this because we're going to start dealing with decimals. And the real meat of what makes today different from yesterday is the use of variables in our expressions for average rate of change. So here's our function, x squared. Find the average rate of change over each of these intervals. And in this case, a is 2 and b is 3. So we need to evaluate f of 2 and f of 3 to set up our average rate of change difference quotient. F of 2 is 2 squared, which is 4, and f of 3 is 3 squared, which is 9. So the difference quotient then would be 9 minus 4 over 3 minus 2. And it may sound a little picky on my half, but I really want to see all four of these things written out as you do your difference quotient. That way I can see where the numbers come from, and when you roll up into the AP Calculus grading schema, they really like to see all four pieces. 9 minus 4 is 5, 3 minus 2 is 1, so our average rate of change on the interval 2 to 3 is 5. Okay. We're going to narrow that window. Instead of going from 2 to 3, we're going to go 2 to 2.5. And that's what we're doing in part B. So again, our A value is 2, but this time our B value is at 2.5, which means our f of 2 is, again, still 4, but our f of 2.5, we would use either a calculator, or maybe you know this, but 2.5 squared is 6.25. So then we set up our difference quotient and we get 6.25 minus 4 over 2.5 minus 2, which is 2.25 divided by 0.5, which equals 4.5. I wonder if you can hear my dog panting heavily in the background. I just took her to the park. Continuing on, we started with an interval going from 2 to 3, and then we went to an interval of 2 to 2.5, and now we're going to a very narrow interval of 2 to 2.1. So our 2 points are slowly approaching one another. So A is 2 in this case, B is 2.1, our f of A is still 4, and our f of B is 2.1 squared, which if we grab our calculators or do it out longhand, we find 2.1 times 2.1 is 4.41. So our difference quotient now would read 4.41 subtract 4 over 2.1 subtract 2. That gives us 0.41 on top and 0.1 on bottom, which is 4.1. And what we can see here is a trend that as our window narrows, our slope changes, and we could perhaps even do the slope from 2 to 2.01 or 2 to 2.00001, and we might see that this number gets closer and closer to some specific value. And in this case, I do know that the value is 4, so it does look like our math is adding up, and part of calculus is learning how to find that value that it's approaching in a much more efficient method than repeating the process over and over again. And the first step in exploring that efficient method is what we're going to see here in part D and E. Part D is a specific case where our initial value is 2, and part E is a more generalized case where our initial value can actually change. And we're not going to get into the exact calculation that I'm talking about today, but we are going to explore doing average rate of change over a variable expression. So in this case, our A value is 2, and our B has a variable in it, 2 plus h. So what this h represents is how wide the interval is. So in the case of 2 to 3, we had a h value of 1. In B, we had an h value of 0.5. And in C, we had an h value of 0.1. And in calculus, what we're going to do is ask the question, what happens as h gets closer and closer to a value of 0? But we're not there yet. We're just going to do the average rate of change. So f of 2 we know is 4. And if we wanted to do what is f of 2 plus h, we'd ask the question, what is 2 plus h squared? And if we expand that out into a polynomial, we'd get our first terms are 2 times 2, our outside and inner terms add up to 4h, and then our last terms when we multiply via FOIL is h squared. So, setting that up, we have our f of b now. F of b minus f of a all over b minus a. And this is the expression that we want to work at simplifying. We see that 4 subtract 4 cancels out, so our numerator, as we simplify it, becomes 4h plus h squared, and our denominator, the 2's cancel, leaving behind just an h. If we were to try to simplify this further, I notice that all 3 terms have an h in it, so the h is going to cancel if I factor an h out of the numerator. And that process of factoring the h out of each of those terms allows me to cancel it out of the numerator and denominator, and we find a final answer of 4 plus h. Now, to show you that this works, in our first case we had an interval of 2 to 3, so that means my h value is 1. 4 plus 1 is 5. In my second case, my interval 2 to 2.5, my h value is 0.5. So 4 plus 0.5 is 4.5. And then in my third case, my h value was 0.1. So 4 plus 0.1 is 4.1. So now we have a singular formula that we could use to do all 3 of these problems much more rapidly. Granted, it took a little bit more algebra up front, but it is nice that now I could ask you very rapidly, what is the answer from 2 to 2.01? Well, if the h value is 0.01, then I'm going to have 4.01. Okay? In part E, what we're changing is instead of starting at 2, we're starting at any arbitrary value a that we want. So in this case, our a value is a, and our b value is a plus h. That way, f of our a value is a squared, and f of our b value, if I FOIL that out, I have a plus h squared, or a squared plus 2ah plus h squared. And now we're going to do the difference quotient on these 4 terms. So we've got f of b minus f of a over b minus a. And this is our difference quotient. It's all variables. But we still probably can simplify things out if we look closely. For example, I notice in the numerator I have a squared minus a squared. So those cancel each other out, and my numerator now has 2ah and h squared. In my denominator, the a's cancel. A subtracts a, and I'm left behind with just an h in the denominator. And finally, like the last problem, all three pieces have an h in it. So if I were to factor the h out of the numerator, I would see the h cancels, and I have an expression 2a plus h. Now this expression can give me the average rate of change starting at any a value and going h units past that a value. So if I wanted to know what is the average rate of change on 7 to 7.3, well, I would stick 7 in for a and 0.3 in for h, and I would get an average rate of change of 14.3. Now, that's not exactly the sort of question I'm going to ask you to do, that last little piece there. What we're going to do is we're going to use these in the future, in the very soon future, to develop the foundation of calculus. And that's how we are extending average rate of change towards the world of calculus. So, the remaining notes for this video are practicing this process with other equations. So it's just extra practice, nothing new. Because these examples are nothing new, I am going to move through them a little more rapidly. I encourage you to pause them and try to tackle them on your own, or at least start them before you take a look at how the video guides us through this. But this time we have a slightly more complex equation than just x squared. We've got this minus 5 and the 2 in there, but it's still finding average rate of change. So our a and b values are 1 and 2, which means to find f of a and f of b, we're going to do f of 1 and f of 2. We can evaluate both of those expressions, and we find that f of 1 is -3 and f of 2 is 3. From there, we can set up the difference quotient of f of b minus f of a over b minus a, and we find the average rate of change to be equaling to 6. Okay. Now we're going to go through the process of narrowing that window. So instead of doing a window from 1 to 2, we're going to do a window from 1 to 1.5. So again, we're going to find our f of 1 and f of 1.5. We plug those numbers into the equation, and we get values of -3 and -0.5. And then with those two values, we set up the difference quotient. F of b minus f of a. Those two negatives can turn into a plus. And after going through the arithmetic of simplifying this, we arrive at an average rate of change of 5. In part C, we're doing it from 1 to 1.1, so there's not much of a change from the previous problem. This time the window's a little bit smaller. I encourage you to pause it. And if we go through the whole process, we arrive at a slope or average rate of change of 4.2. Okay. Now part D is where we introduce the variable, and it's going to add a little more twist to it because we've got that variable in there. But the approach is still the same. We want to evaluate f of 1 and then f of 1 plus h. And f of 1 plus h is going to require us to write out the expression, and everywhere there's an x, we're going to replace it with 1 plus h. When we expand that out and combine all of our terms, the simplified polynomial is -3 plus 4h plus 2h squared. So we're evaluating f of 1 plus h, and we get this. And then we want to set up the difference quotient. F of b minus f of a over b minus a. And this difference quotient should be able to be simplified down as we start to cancel the things that are cancelable. -3 plus 3 cancels, and then the 1 minus 1 cancels. Then we can factor the h out, and the h cancels, and we have an expression now that will tell us the slope from 1 to anywhere past 1. And then part E, same process, but now instead of starting at 1, we're starting at an arbitrary value of a. We evaluate our f of a and f of a plus h. Distribute the 2 in when we're setting our f of a plus h, or our f of b, minus f of a over b minus a. And then cancel the things that cancel. The minus 5s cancel each other out. The 2a's squareds cancel each other out. And the a's cancel each other out. And then we simplify the expression one step further by pulling an h out of all three terms, and we arrive at the expression 4a plus 2h. And the more astute observers might start to see some patterns emerging here from this process. I would suggest you take a look at example 8 and 9 and see if you can identify similarities between the two. As a hint, maybe think about the transformations that happened between example 8 and 9. All right, looking at example 10, the problem is almost exactly the same as number 9. You'll notice the change here is that we have 2x squared plus 5 instead of 2x squared minus 5. And let's see how that plays out. Let's take a moment to calculate your average rate of change from 1 to 1.1. And since it is almost the same, I'm going to move through it rather rapidly. The difference here is our f of b and f of a are, f of b and f of a. Those numbers are different, but when we do the subtraction in our difference quotient, we arrive at the same answer that we had in example 9c. And I want you to think about why we would get the same answer with a different equation. It is kind of a challenging leap of creativity in your math brain, but perhaps you can come across why that would happen. Again, a good hint is think about how we would transform from the function in example 9 to the function in example 10. And how does that transformation affect slope? Okay. 10b, we're looking at the interval from 1 to 1 plus h. So we need to evaluate f of 1 and f of 1 plus h. Distributing our 2. 2 and 5 is 7. 2 and 2h is 4h. 2 and h squared is 2h squared. Then we continue with our difference quotient, setting that up, and canceling the terms that cancel. Here the 7's cancel, the 1's cancel, and we arrive at an expression that we can again pull an h out of the top and bottom. So all three terms get an h pulled out, and we arrive at 4 plus 2h, which you'll notice is the same answer that we found in 9d. So same interval, different equation. Again, why did that happen? Why was there a duplicate solution there? Perhaps we'll see that same thing happen again in part C. A to a plus h. If we evaluate the expression f of a and f of a plus h, we get slightly different looking expressions than in example 9, but the process is still the same. Then we set up the difference quotient, and we cancel the things that cancel. 2a squared, 5 subtract 5 cancels, A subtract A cancels, and we get an expression where all three terms have an h, and so we factor that h out, and we arrive at the same answer that we had in 9e. So this leaves us the question, why did we get the same answer in example 9 that we did in example 10? And I've tried to hint at it. It's not in our notes, but I do want to sketch you a reason why that happens. So, in example 9, we had the equation 2x squared minus 5, which is a parabola that's been vertically stretched and shifted down 5. And I was asking the question, what is the slope from 1 to some arbitrary other location? Maybe it was 1 to 2, or 1 to 1.5, or 1 to 1 plus h. If we take this function of 2x squared minus 5 and turn it into the function 2x squared plus 5, everything gets shifted upwards, including those 2 points that defined the average rate of change. They get shifted up the same amount. If we're going from 2x squared to 2x squared, from 2x squared minus 5 to 2x squared plus 5, everything moved up 10 units. There was no stretching, so our slope between these 2 points did not change. So what we're learning here, and you don't necessarily need to get this concrete in your brain yet, but we're learning that a constant added to the end of the function will not have a bearing on the average rate of change. Okay. I'll write that down if you want to as well. This gets more formalized as we move closer into the calculus side of this thing, but a constant added to a function has no bearing on average rate of change. And this idea of constants going along for the ride, I'm going to say that a lot in calculus class. All right, thanks for watching. Be sure to mash that like button, comment, subscribe. Maybe I'll do a face reveal when I get to 100 subscribers. Or maybe I'll come up with some merch and you can purchase some merch. All right, have a good day.